Okay, so today we'll do some numerical on an important concept, very beautiful concept, that is terminal velocity. Okay, and this terminal velocity concept is linked to your understanding on viscosity and the Stokes law. Okay, so we can, for example, we have a vessel. Okay, we have a vessel. Okay, so let us say we have some liquid in this vessel. Okay, so let me see that I have a ball. Okay, let us say I have a ball. Okay, so this ball, so this ball, it is this ball is falling down. Okay. So this ball is falling down. Okay. So let us say I have a liquid like this. I have a liquid container and I have a ball falling down, falling down. Okay. So if we take the free body of this particular ball, if I take it out, so what are the different types of forces that are acting on this particular ball? Okay. So it will have its self weight. Okay. Uh, Let us say the radius of this ball is, this is a spherical ball. Okay. So radius of spherical ball is equal to, let us say, A, or let us say it is R. Okay. So let us say radius of spherical ball is R, and uh, so what will be the volume of this ball? It is a spherical ball. Okay. So volume of the spherical ball is equal to 4 by 3 pi r cube. So that's the volume. Okay. And let us say the density of this spherical ball material. Okay. So let us say density of spherical ball is equal to, let us say this is rho. Okay. We write it as rho. Okay. So the volume, if this is the volume, then what is the mass? Mass is equal to 4 by 3 pi r cube into rho. Volume into density. Okay, then if this is the mass, then what is the weight?
Into G.
Weight of ball, spherical ball,
Mass into G.
is equal to 4 by 3 pi r cube
Into rho into G.
into G. Okay. So this weight is acting on this ball. This is one force. Okay, one is weight. Okay, and you know, when a solid object is being put on a liquid, it is you have dropped a solid object on the liquid. There will be two forces which will be opposing it.
Yeah.
Okay, one force you clearly know, that is called the buoyancy force.
Yeah.
Okay, so you will have a buoyancy force, which is your FB. Okay, so FB is your buoyancy force. So when a solid body moves in a liquid, there is another force that is called viscous force.
Yeah.
So that's why this Stokes law or whatever. So there will be another force which is your, let's say, let me put it here. We have another force which is your, let us say, FV, your viscous force. Okay. So on this body, there are now three forces. Okay.
Yeah.
One is its weight. Another two forces are your buoyancy force and
Viscous
viscous force. Okay. So what will be the value of this buoyancy force? Okay. So that we have studied. So Fb is equal to your buoyancy force. Buoyancy force. So you know the by Archimedes principle that you know the buoyancy force
The
is
amount
equal
of
to
volume.
weight of the liquid displaced by the body.
Amount of
So the buoyancy force is equal to weight of the liquid displaced by the body. Okay, that's why you say that when you will float, you suppose a big ship is floating on the in the sea. Why? Because the weight of liquid displaced by the ship is more than the weight of the ship. That's why it is floating.
Yeah.
Whereas a
Stone
block, iron block, the weight of liquid displaced by body is less than the weight of the body. That's why it is
Rounded.
not floating. Okay. So what is the buoyancy force? Buoyancy force is nothing but weight of liquid. Buoyancy force is weight of liquid displaced by the body. Okay. So how much weight it will displace? Actually, if we see how much weight it will displace, it is nothing but the
volume.
whatever is the volume of the
of
sphere, that much volume it will displace. Then we will put weight we will consider later. So
First, you should see the volume of the object.
so it's like say how much volume of the volume of the, so it's like first we have to see volume of the displaced liquid is nothing but your 4 by 3 pi r cube again. Okay, that is the volume. Then mass of the displaced liquid, here comes the trick. Here mass will be density of the liquid, not density of the solid ball.
Yeah,
Okay.
yeah. Yes.
Yeah. So you can write density
A fluid.
of fluid, okay, or whatever. It is equal to, let us say, sigma. Okay. So this is sigma. So this mass become 4 by 3 pi r cube into
Sigma.
Okay. Then
Weight will be.
then
G.
weight will be 4 by 3 pi r cube sigma into
G.
Okay. So this is your buoyancy force. Okay. So this value is your buoyancy force, right? This is your FB or buoyancy force. Buoyancy force. Clear? Okay. So now we have got W and we have got FB. W is equal to 4 by 3 pi r cube rho into G. Okay, that is W of ball. Okay.
Yeah.
Then FB is equal to 4 by 3 pi r cube sigma into G. So these are the two forces. Then there is another force which is called your viscous force. Okay. So that is So your FV is equal to viscous force. Okay. So there is a formula for that viscous force. We are not going to derive that formula. That formula is 6 pi. Then n, which is coefficient of velocity.
Yeah.
R is the radius of the ball, and V is the velocity. Okay. So so what happens initially when I put the ball? So initially when I put the ball, some distance, there will be an imbalance between these three forces.
Yeah.
Okay. So what happens? The weight will always remain same. Okay. But the buoyancy force also will always remain same, because your buoyancy force is also, it does not depend on the velocity, but there is one term which depends on the velocity.
Yeah.
Okay.
And here.
So this term initially, so as it goes down, the velocity will go on increasing.
Yeah.
Okay. So here you have the ball at the initially. Okay. So it will have some velocity. Okay.
Yeah.
Then after some distance, it will have the velocity will go on increasing. Let us say it is v here, it will v plus delta v here. Why velocity will increase? Because the downward force is more than the upward force.
Understood.
So there is a net force which causes acceleration, because of which the velocity keeps on increasing as the ball travels downward.
Downwards. Yeah.
But after some time, this velocity will not increase, it will remain constant.
Yeah.
That velocity is called terminal velocity.
Understood.
At that point of time, it will not be accelerating, it will move down at a constant velocity.
Yeah.
That velocity is called terminal
Terminal
velocity. So at that point of time, the three forces
Will be
are in
balanced.
equilibrium.
Will be balanced.
So so the equilibrium equation will be Fv plus F buoyancy is equal to weight.
Well,
Okay, when this
velocity is constant.
so when this condition is met,
Terminal
so why
velocity is
we are
obtained.
saying that when it is going down, the viscous force will keep on increasing. So when it keeps on increasing, at some point of time, this viscous force along with buoyancy
Will
force
be equal in
will just equal to
The weight of the ball.
weight. So that at that point of time,
The
the
velocity
velocity
obtained
is
is
called
terminal
terminal
velocity.
velocity. After that, there won't be any acceleration of this sphere.
Constant velocity.
So that velocity is called terminal velocity. So you can write this equation like, say, if you simplify this one force, so this is one of my force, this is another force, this is another force. Okay.
Yeah.
So this equation can be simplified by writing like, say, 6 pi n r v. Okay, this v is the v terminal velocity. Okay, 6 pi n r v is equal to the weight. Okay, so which is 4 by 3 pi r cube into sigma into g. Okay, so sigma is your density of the liquid.
Understood.
Okay, so sigma is liquid density. So this is your buoyancy force. Okay, so along with buoyancy force, you will have okay, so 6 pi nrb plus the buoyancy force is equal to, so these two forces, viscous force
Plus
the buoyancy force is equal to the weight.
Weight of the
Okay,
ball.
so 4 by 3 pi r cube into rho into g. Okay, so this is the equation. So if you simplify this equation, just if you take this towards
common.
this side,
You have to take common.
if you take this towards this side, it will become 6 pi n r v t
Into
is
sigma.
equal to 4 by 3
Pi r cube
pi r
into
cube.
sigma minus
Hmm.
rho minus sigma.
4 by 3 pi r cube rho minus sigma
Pi r cube g into rho minus sigma.
pi r cube g into rho minus sigma. Okay, so this is the very important equation. So this is the equation. So to find the terminal velocity, you just have to divide this term on the other
It
side.
is constant.
So your equation for terminal velocity will be like this. So your Vt is equal to 4 by 3 pi r q, 4 by 3 pi r q g into rho minus sigma
By 6 by 9.
then that divided by 6 pi nr, 6
NR.
pi n
R. Radius.
r. Okay. So this is very very important. So this is the your terminal velocity. Okay. So from here there can be n number of numerical based on this equation. Okay. So what do you interpret from this equation? Your terminal velocity is directly proportional to r cube.
Yeah.
So if the radius of sphere is very high, your terminal
But
velocity.
RR will get cancelled.
Okay, so r will get cancelled. So r q, so this will become r square. So terminal velocity is directly proportional to r square. So it is inversely proportional to coefficient of viscosity. Okay, so with that, so now you know terminal velocity is directly proportional to r square. Okay, and similarly your terminal velocity is inversely proportional to coefficient of viscosity. So if the fluid is very viscous, your terminal velocity will be less.
Yes.
If the size of the ball is very high, your terminal velocity will be more.
Less. Will be more directly.
Yeah. So this is the, okay, right?
Yeah.
So you can take a picture of this. So now using Stokes law and using the principle of like Archimedes principle
Terminal
and the
velocity.
buoyancy force and knowing the like the
Formula for
equilibrium,
terminal.
the equilibrium, force equilibrium equation,
For terminal velocity.
you are able to derive terminal velocity. Okay, you have taken a picture. Okay, so using this method, now we will solve some numericals on terminal velocity. Okay. Okay. So just remember your terminal velocity is directly proportional to r square. Terminal velocity is inversely proportional to coefficient of viscosity. Okay. Also the density also matters. Okay. That formula also we have the
Sigma
density.
minus
Yeah, the differential density that also matters. Okay. Okay. So one question is two spherical raindrops with radii of ratio 1:2. Okay. So
R1 is not.
so I have a raindrop 1, okay, and which is R1. Okay. I have a raindrop 2, which is radius. Okay. Radius of okay, R2. Okay. So this is R1 by R2 is equal to
1 by
1 by 2. Okay. Fall from a great height through the atmosphere. So atmosphere also air is fluid. So you need not say that it will be liquid. In fluid also there will be, in air also there will be viscous force. Okay. So that viscous force is otherwise sometimes called as drag and all. Okay.
Yeah.
Suppose your aircraft is traveling, it is cutting the air. So there also it is the viscous force or the viscous drag. Okay. Same thing. Okay. So they are asking the ratio of their momentum after they have attained terminal velocity. Okay. So find the ratio of their momentum, let us say momentum is m, okay, after they attain terminal velocity. So you know momentum is nothing but m1 v1.
To V1.
Let us say momentum, I will write
P
small
is
m1.
no, momentum is P. You can represent momentum by P.
Okay, P. So P is equal to P1 is equal to small m1 v1, P2 is equal to small m2 v2. Okay, so the ratio of their momentum is there. So we want to find out the ratio of the momentum, which is P1 by P2, which is equal to m1 v1 divided by m2 v2, right? Because both the raindrop, so let's say this is this and this is this. This is 2 times, okay? So this is 2 times. So this is my raindrop falling. This is my raindrop falling. This is 1. This is 2, okay? So after some distance, they will attain terminal velocity, right?
Yeah.
They will attain terminal velocity. So here this is also terminal velocity. Okay, here this is also terminal velocity. Okay, so I can write it as VT1. Okay, VT1. This is
VT2.
VT2. Okay, so I know that Vt is directly proportional to R square.
Yeah.
Okay, so and m1 is nothing but your 4 by 3 pi rq, right?
Yeah.
Pi r1q into the density, right?
Yeah.
Density of the ball.
Yes.
Okay. Okay. Into Vt1, which is directly proportional to
R square.
square. Then 4 by 3 pi r1 r2 cube. Then this is also rho 2. Okay. Then r2 square. Right?
Yeah.
So this rho 1, rho 2 cancels because this is the same ball. Ball is same, and then this cancels, this cancels, this cancels, this cancels. Okay.
Yeah.
So okay. So what is happening now? P1 by P2 is equal to
R1 to the power
R1 to the power 5 divided by R2 to the power 5.
1 by 32.
Okay. So here the catch is the terminal velocity for both the balls are different because you cannot think the terminal velocity are same. The terminal velocity is different, mass
Because
is
the
also
radius
different.
is different.
So this is nothing but your R1 by R2 to the power 5. Right?
Yeah.
So this becomes
1 by
half to the power 5 is equal to
1 by
32. So P1 by P2 is equal to 1 by
32.
That's the answer. Okay. So 1 by 32 is the answer. So so like this there is another numerical, two spheres of same material but radii R and 3 are allowed to fall vertically towards a liquid of density, so the ratio of their terminal velocity. Okay.
R and 3R.
Uh, so this is very simple one. Here we have gone to momentum.
Here
okay.
only that
Only
R,
terminal
only
velocity.
to the square. You
So
have
let us say one ball is radius r.
to. The other
Okay.
one is 3R.
Another ball is of radius 3r. Okay. So you want to find the ratio of their terminal velocity. So that is Vt1 divided by Vt2, which is then we know terminal velocity is directly proportional to r square. Okay. So it is r1 by r2 whole square.
Whole square.
Right.
Yeah.
And it is being given that r1 by r1 is capital R, 1 is 3r.
3R.
So it is nothing but
R square.
half to the power 1 by 3 to the power square.
Square.
So which is
1 by
it will be 1 by 9. So this is 1 by
9. Yeah.
okay. So these if you know the relationship only, if you know the final equation. See, I have derived it for your understanding, because just by remembering the final formula you may forget sometime. Okay, that's the reason why we have derived, because it is a very important concept. Okay, but finally we have arrived at a equation. Okay, this is my terminal velocity, which is directly proportional to r square and inversely proportional to this thing,
Coefficient of viscosity.
coefficient of viscosity. But so in a viscous fluid, it will more viscous is the fluid, lesser is the terminal velocity. Okay. So now this type of numerical we can, I have seen in every year in JEE there will be one question related to terminal velocity, or what we had studied yesterday on Reynolds number. Okay, less than 1000, 1000 to 2000 to more than 2000. So
Turbulent.
one is steady flow, 1000 to 2000 is steady to unsteady, beyond 2000 it is turbulent. Okay, so Re is equal to rho Vd by nu. So there you have to be very carefully about the unit, because Re is nothing but a number. So when you do the
Simplify, then
division,
it should
finally
get
it should be unitless.
Yeah.
Then only you will be confident that what answer you are getting is correct. Okay.
Yeah.
So we have solved numerical and Reynolds number. Now on terminal velocity.
Yeah.
Okay, which are very two most important concept in your
Fluid mechanics.
fluid. Okay.